Welcome to the video help with physics problems for Physics 1A. This video covers homework set 4, part 1, which is everything under the headings temperature and kinetic theory and the ideal gas. For 1121 students, this is questions 1 to 5. For 1131 students, this is questions 1 to 7. Problem 1. In this problem, we're given the gain of a transistor at a couple of temperatures. We're told that we can assume that the gain is linearly dependent, and we need to work out what the gain is at 28 degrees. Let's write an equation to describe what's happening. We've got gain is equal to some constant times the temperature plus some other constant. This is what we mean by linear dependence. There's a linear dependence here on temperature. It has the equation y equals mx plus b. Okay, so to simplify this, let's call this constant c and this constant k. Now we can write down a couple of equations with the values we're given. We're told that the gain is 30.0 at 20 degrees. So this is c times the temperature, 20.0 plus 273, plus some constant k. Let's call that equation 1. And we're told that the gain is 35.2 at 55 degrees C. So that's C times 55.0 plus 273 plus k. That's equation 2. Okay, now let's solve these equations to find C and K. We can then use that to work out the gain at 28 degrees. Okay, so let's do equation 2 minus equation 1. That'll get rid of these K's here. So we've got 35.2 minus 30, that's 5.2. And we've got C, we can pull this out as a common factor, of 55.0 plus 273 minus this term, which is the 20.0 plus 273. The 273s will cancel out. So this is equal to 55 minus 20, which is 35.0 C, giving us that C is equal to 0.14857. Okay, so we've got C. Now we can get K. Let's substitute into 1. So 1 tells us that K is equal to 30.0 minus C, which is 0.14857, times 20.0 plus 273, which is equal to minus 13.53. Okay, so now we want to find the gain at 28 degrees. So we have the gain is equal to C, so that's 0.14857, times the temperature, which is 28.0 plus 273 kelvins, plus this constant K, which is minus 13.53. Solving that on the calculator, we end up with 31.2. So that's our gain there. Problem 2. This is for 1131 students only. In this problem, we measure the length of a rod with a steel ruler. It's got markings on here, marking off the centimeters. And this ruler is made of steel. The linear coefficient of expansion for steel is given by 1.1 times 10 to the minus 5 per degree C. We measure the rod with the ruler at 20 degrees C. We then heat up the whole thing in an oven to 270 degrees C. And re-measure the rod with the ruler. As these are heated up, both the rod and the ruler expands. So each of these 1 centimeter increments moves along a little bit. We're told that initially the rod is measured as 20.05 centimeters long. And then finally, when it's measured again with the ruler, rod with ruler, it's measured to be 20.11 centimeters long. Now the issue with using this measurement to work out the coefficient of expansion is that this ruler has expanded as well. So this measurement is actually too short because the spacing, 1 centimeter, what used to be 1 centimeter on the ruler is now actually 1 centimeter plus a little bit. And so we've got too short a measurement here. So the best way to approach this question is to first find out by how much the ruler changes. So find out by how much 1 centimeter of the ruler changes. Okay, so the change in length of the ruler is equal to alpha delta TL. That's for anything, and so for the ruler it's 1.1 times 10 to the minus 5, our coefficient of expansion coefficient here. The change in temperature is 270 minus 20, so that's 250, and we're looking at per centimeter, so 1 centimeter. So the change in length, when we do this on the calculator, is 2.7 times 10 to the minus 3 centimeters, and that's for each centimeter. So each centimeter of ruler changes by that much. So 1 centimeter is now measuring, now that it's heated up, 1.00275 centimeters. Okay, so now what we need to do is work out what the actual length of the ruler is, because it's measured as 20.11 centimeters, but the actual length of the rod, is equal to the 20.11, which it's measured at, times this expansion, so 1.00275, because each centimeter expands to this length. When we do that on the calculator, we end up with 20.1653 centimeters. So this is the actual length of the rod. Okay, so now we can work out the expansion coefficient of the rod just by rearranging this equation. We've got the expansion coefficient of the rod is equal to the change in length of the rod over the change in temperature times the initial length. And so the change in length is the final length, 20.1653, minus the initial length, 20.05, over the change in temperature, which was 250 degrees C, times the initial length, which is 20.05. These are in centimeters, but this is in centimeters, so those units will cancel out, and that's fine. Putting everything into the calculator, we get 2.3 times 10 to the minus 5 per degree C. And so that's our final answer to this question. Problem 2 for 1121 and 3 for 1131. In this problem, we're given the composite rod. It's made up of a length L1 of one type of material and L2 of another type of material, and the total length is equal to L. In part A of the question, it asks us to derive an expression for the linear expansion coefficient for this composite rod. Okay, so the change in length of the composite rod is equal to the change in length of the first part of the rod plus the change in length of the second part of the rod. The change in length of the first part of the rod is given by alpha 1 times the change in temperature times the initial length, L1, and the change in length of the second rod is given by L2, change in temperature, L2. So we can write this as delta T, taking that out as a common factor, alpha 1 L1 plus alpha 2 L2. And delta L for the composite rod, well, that'll be the composite alpha times delta T times the initial length L, just from the definition. And so these delta T's will cancel out, and we end up with alpha for the composite rod is equal to alpha 1 L1 plus alpha 2 L2 over L, where L is L1 plus L2 if we wanted to substitute those in. Okay, part B, we're now told that we're using a rod made of steel. So this is steel and this is brass, so let's call that LB, length of brass. And we're told that alpha for steel is equal to 1.1 times 10 to the minus 5 per degree C, and that alpha for brass is equal to 1.9 times 10 to the minus 5 degrees C per degree C, and that the length of this rod L is equal to 52.4 centimeters. And we're asked what's the length of steel and what's the length of brass that we need to make up this composite rod, and the composite thermal expansion coefficient is given by 13 times 10 to the minus 6 per degree C. Okay, let's write down a couple of equations to describe this. We've got L is equal to L steel plus L brass. That's equation 1. That's obvious from this diagram. Equation 2, we'll just substitute everything in here. And so we've got 13 times 10 to the minus 6 is equal to alpha of steel, which is 1.1 times 10 to the minus 5, length of steel, plus 1.9 times 10 to the minus 5 times the length of brass, over the total length, which is the 52.4. Okay, so let's rearrange this one. We've got L is 52.4, so that tells us that the length of steel is equal to 52.4 minus the length of brass. So we can substitute this in for the length of steel in this equation. Let's multiply this by this to get it out of the way. So we've got 6.812 times 10 to the minus 4 is equal to 1.1 times 10 to the minus 5 times the length of steel, which is 52.4 minus the length of brass, plus 1.9 times 10 to the minus 5 times the length of brass. Okay, so expanding these brackets and moving this term over to this side, we end up with 6.812 minus 5.764 times 10 to the minus 4 is equal to the length of brass times 1.9 times 10 to the minus 5 minus 1.1 times 10 to the minus 5. Okay, so that tells us that the length of brass is equal to 1.048 times 10 to the minus 4 over this, which is 8 times 10 to the minus 6. Solving that on the calculator, we get 13.1 or 13 centimeters to two significant figures. And so then substituting back into here, 52.4 minus 13 gives us 39. And so the length of the steel is equal to 39 centimeters. Okay, so we've solved that problem. Problem 3 for 1121 or 4 for 1131. In this problem we have weather balloon. Initially it's down on the ground and it has a pressure of 1.00 atmospheres, which is 1.01 times 10 to the 5 pascals. Its volume down here is equal to 3.47 meters cubed, and its temperature is equal to 22 degrees C. It then rises up into the atmosphere where it expands. It's now at a pressure of 36.0 centimeters of mercury. Okay, if we want to convert this into pascals, we actually need to multiply it by a conversion factor, which you can look up. It's 1,333. So when we do that on the calculator, we end up with 4.77988 times 10 to the 4 pascals. At this height, the temperature of the atmosphere is minus 48 degrees C, and we're asked what's the volume now. Okay, so we can just use the ideal gas law, PV is equal to nRT, where the balloons are completely sealed, so N is not going to change, R is the gas constant, so it's also not going to change. So these two things will be constant, so we can write PV on T is equal to a constant, which tells us P1V1 on T1 is equal to P2V2 on T2. And so we can substitute everything in here. Just remember that the temperatures need to be in kelvins, not in degrees C. So we've got 1 atmosphere, 1.01 times 10 to the 5 pascals, times the volume down here, which is 3.47 meters cubed, over the temperature down here, 22 plus 273, is equal to the new pressure, which is the 4.7988 times 10 to the 4 pascals, times the new volume, which is what we're trying to find, over the new temperature, which is 273 minus 48. Solving that on the calculator, we end up with 5.57 meters cubed. So that's the new volume. Problem 4 for 1121 or 5 for 1131. In this problem, we've got hydrogen molecules colliding with a wall. So they're coming in. Their velocity coming in is given by 1.0 times 10 to the 5 centimeters per second, which is equal to 1.0 times 10 to the 3 meters per second. And then they hit the wall at an angle of 55 degrees with the normal. And then they will rebound off. As this is a gas molecule, we assume it rebounds with the same speed, so it's 1.0 times 10 to the 3 meters per second. We're told that the mass of hydrogen is equal to 3.3 times 10 to the minus 24 grams, which is equal to 3.3 times 10 to the minus 27 kilograms. And that 1.0 times 10 to the 23 hydrogen molecules strike the wall each second. And the question asks us to find the pressure that they exert on the wall. Okay, so pressure is equal to force over the area. So we're told in the question that the area of the wall is 2 centimeters squared. So what we need to do is work out this force. Now, the impulse is equal to force times time, and it's also equal to the change in momentum. Now, as the molecules come in, the vertical component of their velocity is not changing, that's remaining constant. It's just the horizontal component which is changing. So this is equal to the V final minus V initial. But when we're considering V final and V initial, we only need to consider this horizontal component, as the vertical component stays the same. Okay, so the force in 1 second is equal to the mass hitting the wall in 1 second. So that's 3.3 times 10 to the minus 27 kilograms. And there are 1.0 times 10 to the 23 hydrogen molecules. So this is the total mass hitting the wall in 1 second. And the change in velocity is equal to 2 times 1.0 times 10 to the 3 times, we only care about the horizontal component, so cos 55. So 2 times 1.0 times 10 to the minus 10 to the 3 cos 55. The 2 times just comes about because they have opposite directions but the same magnitude. So this is the force per second. And so solving this on the calculator, we get 0.37856 newtons. And so the pressure is equal to 0.37856 newtons over 2 per centimetre, which gives us 0.19 newtons per centimetre squared. Sorry, that's in meters squared. The more normal units is that's 1,900 newtons per metre squared. And newtons per metre squared is equivalent to pascals. So that's 1,900 pascals, which it's exerting on this wall. And 5 for 1121, 6 for 1131. Okay, now we have a steel tank. We're told that it has ammonia in it, so it contains 315 grams of ammonia. The pressure is measured at 1.35 times 10 to the 6 pascals, and the temperature is equal to 77.0 degrees C, which is equal to 77 plus 273 kelvins. And now in part A, we're asked what's the volume. To answer this, we'll need to use the ideal gas law. PV is equal to nRT. So we know the pressure, we know the temperature. What we need to start off working out is the number of moles. So we can actually work out the number of moles using this mass here, because there's a relationship between the number of moles, the mass, and the molar mass. So the number of moles is equal to the mass over the molar mass. So this is 315 grams. Now the molar mass of nitrogen is 14 and of hydrogen is 1. So there's 3 hydrogen molecules. So the number of moles is 315 divided by 17. Doing that on the calculator, we get 18.5 moles. Okay, so now we can substitute in and find our volume. So volume is equal to the 18.5 moles times the 8.314 times the 77 plus 273, that's the temperature. And then we need to divide all that by the pressure, which is the 1.35 times 10 to the 6 pascals. And that gives us 0.0399 meters cubed. Okay, part B, we now said that we're told that the tank's later checked and the temperature's dropped, so the temperature is now equal to 22 degrees C, and the absolute pressure has fallen, so the pressure is equal to 8.68 times 10 to the 5 pascals, and we're asked how many grams have leaked out of the tank. So the number of moles between part A and B is not constant. What we need to do is find out by how much the number of moles has changed, and from that we can calculate the mass which has leaked out of the tank. Okay, so the final number of moles is equal to, just rearranging this equation, we've got the pressure, 8.68 times 10 to the 5, times the volume, which is calculated here, 0.0399, times R, which is 8.314, times the temperature, which is now 22 degrees C, so that's 22 plus 273. Solving that on the calculator, we get 14.11 moles. Okay, so let's continue up here. The change in the number of moles, the initial moles minus the final moles, is 18.5 minus 14.11. So the change in number of moles is 4.38 moles. So that's how many moles have left the tank. We were asked for the mass. So the mass is equal to 4.38 times the mass of 1 mole, which we said over here was 17. So solving that on the calculator, we end up with 75 grams. So 75 grams of ammonia has leaked out of the tank. Problem 7 for 1131 only. In this problem we have a hot air balloon. The hot air balloon has a mass of 249 kilograms and it wants to lift a load with a mass of 272 kilograms. The volume of this part of the hot air balloon that holds the gas is equal to 2,180 meters cubed. It rises up into the atmosphere until it's surrounded by air with a density of 1.22 kilograms per meter cubed. While it's doing that, it's being heated, so the temperature of the air in here is changing. The temperature of the air outside is 18 degrees C, which is equal to 18 plus 273 kelvins. What we're asked to find is what does this temperature need to be to let the hot air balloon lift this load. Okay, so to answer this question, we're going to need to use Archimedes' principle, which is that the buoyancy force is equal to the weight of the, well, in this case, the air being displaced. Okay, so the required buoyancy force needs to lift its own mass plus the mass of this load. So the required force is 204, well, let's just do this with symbols, mb plus ml times g. And the weight of air being displaced, let's let the air in here have a density rho 1. So the weight of air being displaced is rho naught, the external density, minus the internal density. Now to get from a density to a mass, we need to multiply that by the volume, which will just be the volume of this balloon, and then by g to make it into a weight force rather than just a mass. Okay, so you can see these g's are going to cancel out. So in this equation, we know everything apart from rho 1. So we can use this equation to work out the density of the air in the balloon. Once we've got the density, we should then be able to work out the temperature. Okay, so let's substitute in. We've got 249 plus 272 is equal to 1.22 minus rho 1 times 2,180. Okay, so add these together, divide by this, and then rearrange to get rho 1. When we do that, we get rho 1 is equal to 0.981 kilograms per meter cubed. Okay, so now what we need to do is we need to use this to find the temperature. So to do that, let's make use of the ideal gas law. We know that PV is equal to nRT. Now, when this balloon's up in the atmosphere, molecules of gas can come in and out, so N's not constant. T is what we're trying to find. R is a constant. The pressure is imposed by the surrounding atmosphere, so in that case, the pressure inside and outside the balloon is constant, and volume is fixed by the volume of the balloon. So we can write this as NT over V is equal to P on R. These were both constant, so this is constant. Otherwise, we can write it as N naught T naught over V naught is equal to N1 T1 over V1, where T1 is this temperature. Okay, so now we need to use this density. So density is equal to the mass over the volume. So inside this, the mass of air is given by the number of moles of air times the molar mass of air over the volume. Okay, so a useful way to write this is in our equation we've got N on V. N on V is equal to rho on M. Okay, so let's substitute in here. Where's the room? Let's write this down here. So instead of N naught on V naught, we've got P naught on M. Well, this is the molar mass of air. Both these are air times T naught is equal to, instead of N1 on V1, we've got rho 1 on the molar mass, and once again this is air, so this is air, T1, so the molar mass of air cancels out, and we end up with P naught T naught is equal to rho 1 T1. And so solving this for T1, which is what we're trying to find, we have rho naught, which is the 1.22, times T naught, which is the 18 plus 273, over rho 1, which we found up here at 0.981. And this gives us a final answer of 361.9. And that's in kelvins. So just subtract the 273 from that, and we end up with 88.9 degrees C.